into this, we call it a PN junction. So what is going in there? So here we have the N material, here we have the P bulk material. So you can remember on this side we have some free electrons. On this side we have holes. So we need some electrons here. Yeah. And what will happen if we bring these two materials in close contact? Then the electrons of the N side will actually go to the other side. They will diffuse to the other side and saturate and missing link out of this structure here. You have to remember that both sides are electrically neutral. So on both sides we have the same amount of protons and electrons, so that's neutral. So if we do an N doping, that does not mean that we have more electrons than protons. The number of electrons and protons is always the same and it's neutral, the material. But now, if the electrons from this side move to the holes of the P side, then here we have an area
of missing electrons.
And this area here exhibits a space charge. Rho, space charge. What kind of charge do we have on this side? If the electrons disappear or positive to the other side, we have a positive charge here. And on the other side,
a negative charge.
We have a negative charge because we have more electrons than protons.
Yeah. But why the protons don't move to the
The protons never move because in the movement of the protons, this would mean that the whole atom has to move because the protons are in the core of the atom. Thank you. And this will mean that the whole lattice structure must be changed, and that's not possible. Huh? So only the electrons move. So that means that on this side we have a positive space charge, and on this side we actually have a negative space charge. That means that we also have an electric field across our junction. Yeah? Positive, that's where the field vector starts. Negative, that's where the field vector ends. So that means we have an electric field across our junction. And this electric field finally stops the diffusion of the electrons from the N side to the P side. So after a while, the diffusion comes to a stillstand or a standstill, and we now have stable conditions. That's when you take a diode without connecting any power source, and you have these stable conditions here. You have an electric field within this PN junction without any attached power source.
That what makes it a conductive material, right? This area.
Now this area actually here is insulating. The bulk material is a conductor. It gives you the resistance of the bulk material. Yeah? That's a couple of ohms. This N or P doped areas, this is a bad conductor. But since that this is very small, the resistance is not big. It's in the area of ohm or sub-ohm area.
So the big that area is, the less conductivity the material is.
How big this space charge area
The more
groups,
resistance.
this depends on the doping factor. Yeah?
The dop.
For a mild doping, this area will get bigger. For a hard doping, so if you have a huge number of
Neutrons.
electrons here and of holes here, then this area gets smaller. And this defines a replication. Yeah? If this space charge area is quite big, then your diode is for high voltage applications. But for high voltage application, there you also have that the diode cannot carry that much current. And if this area is rather small, then it's for low voltage applications and high current. Yeah.
How can we characterize fast doping?
How can we characterize
The fast doping? How do we know that we have
the doping? That depends how many atoms you implant into the silicon wafer. The more you implant, the higher the doping rate gets. Yeah. But and now we came to the function of the diode. What is a diode famous for? What is the primary application of a diode?
When we want to make the electron in one direction and in one path, in order to don't get it back to the source,
Yeah.
you go only to the destination.
Yeah. So that's one application. This here. So one application is to control the current flow. Current flows only in one direction. Yeah? So that's what we call rectification. And that's what the sign, the circuit diagram sign of a diode means. Current can only flow in one direction. Is there any other application?
don't let the current to come vice versa.
Yeah, that's that. Current flows only in one direction.
For preventing about the input of the electricity flow to the device. A kind of protection.
Yeah, but that's also rectification, more or less. Huh? So current flows only in one direction, the other direction is blocked. But there is one very important application of the same structure.
If we break the current, then the current will start from the source, or when we break from at that point of view,
Yeah,
we
But-
stop the current.
we stop the current, but that's all. I would also summarize under rectification. Current flows only in one direction.
Yeah, it's flowing from source to destination.
Yeah.
We stop the current in between some source and destination. Again, the current will start from source or in between where we stop.
I don't understand you quite, but I think this is also rectification. So the diode controls the current flow. But is there any other application? Think about this PN junction. Yeah? Is there any other application of a PN junction? And I don't mean a transistor. Transistor is also a PN junction, but just the P and the N structure, you combine it. Do you have any other, or is there any other application for that? It's getting more and more popular nowadays.
To sense that, is there any flow?
The PN junction can, this is, now we have spoken about the PN junction as a device for controlling current flow. But the PN junction can also work as a source of power. And that's what we call a solar cell. But it's actually more the same physics. You can use this PN junction as a diode for controlling the current flow, or you can use the PN junction as a solar cell. Yeah? It's more or less the same physics behind these tools. First, we will focus on the first application. What is going on here? So that the main thing is this internal electric field of this space charge area. That's what is defining the properties that current can only flow from one side to the other side. So now we have to think about current flow. That means that we put some metallic bonding on the PN structure, on the bulk material. And here we can connect our power source. And if we connect the power source in a way that we're talking about now about electron flow, that the electron will move this way, draw it in red. So these electrons are electrons from our power source. These electrons will come through the bonding material into our silicon crystal, and these electrons move this way. And what will happen here? Here we have an area with no electrons, because the electrons from here they have diffused to the other side, and they are setting up this electric field.
But there is protons here.
There are protons here. Yeah. They are all the time here.
Yeah.
They won't move. And these electrons, if we are now connecting our p-n junction just in a manner that we have, there is our source, and the electrons are moving in this direction. The electrons can move through the bulk material because there is minimal resistance here. And they move that far that they came to the space charge area here. And here there are no more electrons. That means that the first electrons, they come in here, they saturate with the holes that were created when the original electrons moved to the other side. But the more electrons they come to the space charge area, the more of the holes get cancelled out. And if there are enough electrons from this side, then the electrons can move across this area here, across the space charge area, and they get into the p material, and so the circuit is closed. That means that the electron can move
through the protons.
This circuit through our p-n junction
and through the protons area.
Don't think about the protons.
Okay.
It will give you wrong results. So forget about the protons.
Okay.
Within semiconductors, the main important thing are the electrons.
Okay.
And only the electrons are moving. The protons are where they are, and they never leave their location. Yeah? It's true that there are a lot of protons in here, but they don't
Affect on
the
any.
current.
Okay.
Conversion, yeah. So the electrons, if they are delivered from that side, they saturate all the holes on this side here, and when all the holes are saturated, then also this electric field vanishes. There is no electric field, and the other electrons can pass nearly without resistance. But the effect of our electric field that's generated by combining an N and a P material is that we have some losses across our junction. Yeah? So across this p-n junction, we all the time have losses into the electric field. And the electric field emanates from the diffusion of the electrons from the N to the P area. and the amount of electric field is characteristic for the semiconducting material. So for example, for silicon or gallium arsenide, whatever you use. So that means that you have some losses across your junction. Huh? So it's not an ideal rectification. But if the electrons move the other way around, so maybe if it was supposed to be a new one, but actually not. But if the electron moves from the other side, so if we change our current direction, if the electrons move from that side, then here we got a lot of electrons. That means we have some more electrons. That means that the electric field will even grow. Yeah? So the electric field will grow and the space charge area widens a little bit. Yeah? Because if we are pumping in electrons here, then that means that from the other side the electrons are extracted. So this positive charge here gets even bigger, and the negative charge on this side here even gets bigger. That means that our space charge area widens a little bit, but nevertheless it's not possible for the electrons to move in that way. Yeah? It's not possible for the electrons to get across the junction. Yeah? So in the green direction there is no current flow. And
Why I
that's...
do that?
Sorry?
And why I do that in the other direction? Only to widen the electron field? Or?
No, that's part of the game of the rectification.
Ah, okay.
Yeah? So maybe if you have some AC voltage and you want to get some DC voltage out of the AC voltage, then you need, that's a simple application of the diode.
Ah, okay.
That we also can try in the lab, but seen from outside of the semiconductor device, that means that the current, the technical current, can only flow in this direction, because technical current flow direction is opposite to the electron flow direction. Yeah? So the electrons flow in this direction, the technical current flows in that direction. So that means that technically the current flows from the P to the N side. So that means if you got a P and an N area, then that corresponds to the circuit diagram in that direction. And the arrow always points in the direction of current flow. So with the circuit diagram it's quite easy. Current flows in that direction. Yeah. That's the one major application of a PN junction, rectification. An application circuit, a simple application circuit that we can build in the lab. Is we have a generator. It generates some AC voltage. We got our internal resistance, because every source, like we knew from the last time, has an internal resistance. And if we would like to transform this to a DC voltage, then there are different kind of circuits, but the simplest of all is just put a diode here and a resistor and maybe a capacitor, our load resistance and capacitor. So if we put a probe on here, and this is our ground reference, this is ground, this is our reference, and if we put a probe here, say 1, then the voltage will look something like this. And after the diode, we have some losses. We have said we have some losses, and they stem from the
PN,
diffusion potential or the
PN junction.
electric field of the
Yeah.
PN junction. It's called diffusion potential.
Fusion potential.
And this sums up roughly to 0.6, 0.7 volts. That means if we have 1 volt peak here, across the diode we roughly lose about 0.6 to 0.8 volts. It depends on the current flow. So on the other side here, if we put the probe in now here, we lose 0.6 volts. So what we are seeing is something like that
Small peaks.
during the conduction, and in the negative direction we don't have any current flow, so we see voltage 0. And if we also implement the capacitor here, then this will sum up to something like that. And this is nearly, it definitely is a DC voltage because it doesn't change the sign, and it's roughly flat. Yeah, it's not perfect, but
It's flat or have a minus degree.
this is a what we call an E-potential decharging curve.
So each time.
Yeah. And here we recharge the capacitor, and then we decharge it, recharge it, decharge it. And the bigger you make the capacitor, the more it flattens out. Yeah. So by now you should know what the physics behind this PN junction. And that's a simple application circuit. We can put to life in the lab. This is the generator. It generates our AC voltage. For a diode, you can use a 1N4007 or something like that, doesn't matter. Because every silicon diode exhibits the same characteristics. And how does the characteristics look like? That's the forward area. That's the conducting area. And that's the reverse area. So that's when the diode, when there is, or when there ought to be no current flow. But there is still a minute current flow. So in the forward direction, there is an exponential rise in current. And there is Shockley's law of diode current. So the forward current is equal to a saturation current that depends on the manufacturing process times E raised to forward voltage over the temperature voltage times a modulation factor M minus 1. This minus 1 gives you 0 current if you have 0 voltage. Because if you have 0 voltage, E raised to the power of 0 is 1. And there is no current flow, definitely no current flow if there is no voltage across the diode. Yeah. Because we have said that, then you have stable conditions within the space charge area. And in the reverse direction, the current flow is nearly 0. That's the reverse current and the reverse voltage. So in reverse direction, the diode is nearly ideal. But in forward direction, you see, there is some voltage drop along the diode. So it's roughly 6.0 to 0.8 volts.
During the voltage drop, do we also have flow of current?
The voltage drop is due to the diffusion potential or the internal electric field.
Yeah, at that point, do we have flow of current as well?
The voltage drop is exactly across here. Yeah? With every current flow. Yeah? If there is a current flow maybe of 1 amp, then your voltage drop is maybe 1.2 volts. If you have only a current flow of 10 milliamps, then you have only a voltage drop of 0.6 volts or less. Yeah? So this is a non-linear component, a diode. Yeah? That's why you could not make any more calculations with Kirchhoff's law or Ohm's law or something like that. Yeah? That's not possible. Because this is a non-linear element. So that's when we are using the PN junction as a rectifier. And the second application is if we are using the PN junction as a power source, then we are calling it a solar cell. But nevertheless, it's the same physics behind that. It's the same junction. The only difference is that we exhibit the junction to light, sunlight. Yeah? So that the sunlight directly can shine into the junction. And that's what you see with the solar cells. These are the blue cells. That's a big PN junction. Yeah? And what happens then? So if a photon is entering into the PN junction, and if the photon is hitting the PN junction, it generates a charge carrier pair, it generates an electron and a hole. Due to this diffusion potential or the inner electric field of the PN junction, this charge carrier pair gets separated and it gets out to the boundaries of the space charge area, and there it can freely move through the bulk material, and that's what we call a generator. Yeah? So where will the electron move to? The generated electron, where will it move to?
To that the generated electron?
Yeah. If the photon hits our PN junction, then this energy of the photon generates an electron and a hole, That's the inner electric photo effect.
Yeah, the electron will go that way and the hole will go that way.
The electron will go that way.
Yeah?
And will go in the hole, so the hole won't.
So
Now they get separated. Because if the electron gets into the hole, then
Nothing happens.
nothing happens.
So that's it.
There is a certain probability that the electron gets in the hole, but it's rather low. Normally, the electron at the hole gets separated.
first, I think first electron goes to the negative part, and then and the holes goes to positive part, and back. And after that, the action of throwing the electron to the hole.
So think about what do we have here on this side of the PN junction.
We have here negative
We have here the electrons
yeah.
that have diffused from the
yeah.
N
Uh-huh.
material. So here on this side we have a lot of electrons.
Yeah.
And would the electron join the other electrons, or
Go for the opposite charge, I think.
it will go for the opposite charge? So it will go to the other side,
Yeah.
and the hole will go to this side here. Huh? But is the hole actually traveling?
No.
No.
You said the proton
There is
does
some electrons from here is actually traveling
to the to the hole.
Huh? The holes never move.
Uh-huh.
There is no hole movement.
So it's actually the what is happening in that the number of electrons increases in that case, right?
The generated electrons is a photoelectrically generated electron. It goes to this side here. Huh? And here it's in the N area. And in the N area it can freely move.
Because there is another
Because
electron.
there are no holes that will suck up the electron.
Uh-huh.
So the electron can freely move up through the whole bulk material to our bonding material.
Uh-huh.
And then it can move into the outside world.
Uh-huh.
And the hole will travel to this side here. This is the P material. We have a lot of holes here anyway.
Uh-huh.
So every electron that enters on this side will get sucked up by the holes. That means we have an electron movement in the outside world from this to the other side.
Uh-huh.
So at this time, the PN junction works as a generator. And the current direction of a generator is always in the reverse direction as the current direction of a load or the sink. That means if we put enough sunlight onto this PN junction, we can photoelectrically generate electron flow or current flow. And that's the principle of a solar cell, where you can produce power. Yeah?
So it's nothing with the heat.
It's nothing with the heat.
Okay.
If you heat a solar cell, the best it can reach is that it will destroy the cell. But there is some specifics to the incident radiation. Yeah? What's the energy that is linked to our quant, our photon that's entering the junction? So for silicon we have a certain energy level that you have to, that's linked with the conduction band and the valence band. For silicon, to get an electron from the valence band to the conduction band, did we do this last time or no? We do it now. So normally in the atom you have discrete energy levels, yeah? Linked to each sphere. And if you put all the atoms together into a crystal, then these different energy levels, here you have the core of the atom, and with every sphere you have some energy levels. A0, A1, A2, A3, E4. It depends how many spheres you have.
The number is maximum is E7, right?
Yeah. And in the outer, and the number of electrons in the outer sphere define the electrical properties of them, as also the chemical properties. That's where this group come in. Yeah? It's from 1 to 7, and 8 is the next group, then we start with 1 again. Yeah? And if you put this atom into a crystal, so that every atom has its neighbor, then these energy levels are not discrete anymore. They get a little bit vague. So then it's a conduction, what we call a conduction band. And this is here that translates to this. But the lowest energy level gives you the upper edge of the valence band. So that translates to here. And the upper levels define the conduction band. And for silicon, there is a gap of 1.1 electron volts. That's a unit of energy. What is an electron volt?
Oh, we had just last time. It's
It's a
10 minus
energy.
10.
It's an amount of energy. But what is an electron volt? How much energy is it?
Yeah, it's 10 times 10 power minus 13, something like that. Ah, that's the charge of the electron.
So an electron volt, the easiest you can remember, have two plates, one at ground potential, one at plus 1 volt. And now let an electron start to move from here, because there is an electric field of 1 volt per the distance. And if the electron travels from here to here, it gathers some energy out of the field. And if the electron hits this side here, it has gathered an energy of 1 electron volt. One electron travels through a field of 1 volt per this distance, and it gains an energy of 1 electron volt. It's very low amount of energy, but still
Countable.
And this is the gap of between the valence band and the conducting band for silicon. If we are talking about an insulating material, this energy gap may be 4 or 7 electron volts, so it's up here somewhere, the conducting band for an insulating material. That means that it's nearly not possible to get from the valence band to the conducting band. That means there are no free electrons in an insulating material. And for a metal conductor, these two bands overlap. So that it doesn't need any energy to get from the valence band to the conduction band. The valence band means that all the electrons in the lowest possible energy states. And if you heat the atom, then some electrons get to higher energy levels.
So the heat affects on the conductivity of the material.
The heat affects the conductivity of a material. With a metal, it's the other way around. But with a semiconducting material, the more you heat the material, the more conductivity you will get.
But with the metal is different.
With the metal, it's different. That depends on the conducting principle of the material. But with a semiconductor, the more you heat it, the better the conduction will get. Because the more you heat the material, the more electrons are in the higher energy levels. That means they are already in the conducting band. Okay. So yeah, we were with the solar cells, and not every kind of energy that hits the p-n junction will generate an electron hole pair. This depends on the energy gap of the material. Yeah? What kind of energy is linked to radiation? Do you have any idea?
No idea.
It's quantum physics.
Solar energy.
So what is light? Basic question. Yeah. So what is your idea of light?
It's a heat.
Heat, yeah. You are stuck with heat and protons. But that's okay. But it's heat. It's not wrong. It's heat.
Okay.
Kind of energy, for example, which drive from an explosion of an atom.
Yeah. Explosion. Okay, but exploding material normally
Yeah.
generates light as well. Yeah.
It is a whole-
But what is light?
it is called
Radiation. But what is radiating?
electron.
Electrons. Is there some electrons? For example, we got the sun, a little bit far away, but it generates light, obviously. Huh? And somewhere we got the Earth, a little smaller than the sun. How big is the distance? Any idea?
That's big.
Big? Yeah. How long takes it for the light to get from the sun to the Earth?
8 minutes.
8 minutes.
8 minutes. Huh? And how fast is the light?
3,000
300,000
kilometer per second.
per second. So we actually can calculate the distance. So it's something around 150 million kilometers. But what is traveling?
The light.
The light. Yeah. What is the light? Is this
Form of energy.
matter or is this just energy or
It's a
It's
form
an-
of energy.
it's a
It's
form
an-
of energy? Yeah. Where is it? And is all the light equal, or is there some, or are there different kinds of lights? So what I mean is there's green, there's blue. So what's the difference between green and blue?
Yeah, I know that.
There's a spectrum, yeah. So that's what we are drawing here. Spectrum. So what's the difference between green and white light? or
It's
blue
for the
light?
frequency, I think.
The frequency, yeah. Is there actually white light?
No, the light is 7.
Light is
It's
from
It's
every, the combination of all of the light.
yeah, 7 colors, the rainbow colors.
The rain, yeah. But it's enough if you get red, green, and blue. At least white is no color. It's just an illusion of our eyes.
That's new.
But there is no white light. So, but we got in our spectrum. So let's say we draw the spectrum according to the wavelength. So is got red or blue the higher, the bigger wavelength?
No, please no.
Is red or blue with the
Red.
longer wavelength?
The red, I think.
The blue one.
Oh, the blue one. Okay.
The red got the longer wavelength.
Okay.
Blue got the higher frequency. Yeah?
Okay.
So maybe if
Lambda.
not to have too much confusion, we draw it here with frequency.
The wavelength is lambda, right?
The wavelength is lambda. It's C, now, what is C divided by the frequency? I think, yeah?
Yeah. What
So
is
the higher the frequency, the smaller the
Smaller.
wavelength. But maybe we stick here to wavelength, because otherwise I cannot give you numbers, because it's pretty uncommon to give frequencies of light. So we have the wavelength. So what's the frequency of light?
Excuse me first, what is C?
That's the speed of light.
The speed of light, okay.
Frequency.
0. I don't know if this, is it correct? It's meters per second divided by 1. It's okay, yeah. So if we stick to red light, then we got a wavelength roughly of 800 nanometers. So let's say it's red. Shorter wavelength, we got red here. So we got 800 nanometers. And for blue, any idea for blue? How much do we have? Is there much difference between red and blue?
Yeah, we said that
No.
the red is more frequency, so it's less wavelength.
And blue
And
is
blue.
more frequency.
Excuse me.
It's on the height.
So it's roughly around 400 nanometers.
The
So
half of
these
it.
are the numbers you should remember, because this is,
It's important.
yeah, that's common knowledge, I would say. And here, what do we got here? If the wavelengths get shorter,
The yellow one?
the yellow is in here. So that's the visible spectrum. From blue, there's here we got violet. It's a little bit shorter than 400 nanometers, 380, where we start with visible light. But below visible lights, there we got the violet. It's called ultraviolet. Huh?
Ah, yeah.
UV, you know. Huh? And if the wavelength gets longer than red, it's
Ultra red.
ultra-red, but it's called infrared.
Infrared, yeah.
Because normally it's seen from the frequency side, and below red it's infrared, and higher than violet, ultraviolet. But if you draw it from the wavelength, you're quite right, it should be ultra-red and infraviolet.
Okay.
But don't confuse the others if you use
Okay.
this expression. And here, what's shorter than ultraviolet? Do we also have some radiation in a technical sense? That's shorter than ultraviolet? X-rays, yeah? And then it's getting shorter and shorter. X-ray will kill you, but what definitely will kill you is cosmic rays. And that's all below X-ray.
Cosmic rays is like gamma and alpha and
Yeah.
this?
Nah,
Not
gamma
alpha.
and alpha. Alpha it's if from a core separation,
Mm-hmm.
an atomic bomb.
Uh-huh.
That's alpha radiation. But this is different.
And gamma also?
Gamma is here, yeah? Gamma is the cosmic radiation, yeah? So gamma, X-ray, ultraviolet, violet, blue. Green is in the middle. Green is where the human eye has the greatest sensitivity to, so it's green.
What is the wavelength for this one?
For green it's around 590 nanometers. So in the different shades of red, so red starting from 800 to 700, so that's a different shade. Then we go to yellow, green, blue. And here we got infrared, and below infrared, that's a long way. Then we come to the ISM bands. So it's 1 to 6 gigahertz. So that's the technical bands for telecom. But it's a long way from infrared to the telecom bands.